Module 4, Comparing Disease Rates. Quantifying disease occurrence is central to epidemiology. Counting the number of cases in a population is the simplest method of quantification. But last week we determined that we need to report frequency measures such as incidence rates, prevalence, and mortality rates, rather than simple counts, in order to take into account possible differences in population size and duration of the study when comparing disease burden between groups. Today, we're going to think about taking into account other possible differences in characteristics between groups being compared, such as age and sex. Is the incidence of disease A increasing? Does disease B occur more frequently in my local community? Does the incidence of disease C correlate with a suspected causal factor? Has the frequency of disease D changed since the implementation of a primary prevention program? To answer these questions, we need to compare two sets of disease rates and be able to interpret the similarities or differences we observe. For those of you who've spent time working in a lab, you'll know that when conducting experiments, you alter only one variable at a time, so that any effects you observe can be attributed to the variable that you've changed. Epidemiological studies are conducted in the real world with real people, so it's difficult to simulate this lab environment and only alter one characteristic at a time. We're often interested in looking at specific factors and observing how they are related to an outcome, most commonly a disease. And the groups of people that we may wish to compare can differ in many ways. Some of these ways we know and some ways we don't know. Therefore, we can't be certain that the observed differences in disease occurrence are due to the risk factor under study or these known or unknown other factors. These other factors are said to confound the association under study. A confounder is something that may be related to both the hypothesized risk factor under investigation and the outcome, usually a disease. As such, it muddies the water when you're trying to figure out exactly what causes what. For example, several studies have indicated high rates of lung cancer in chefs. Though this could be a consequence of their work, perhaps caused by carcinogens and fumes from high-temperature frying, it may be simply because professional chefs smoke more than the average. In other words, smoking may confound the association with cooking. Two common confounding factors are age and sex. In this example, crude mortality from all causes in males over a 5-year period was higher in the British coastal town of Bournemouth at 1,694 deaths per 100,000 males, compared to the coastal town of Southampton with a mortality rate of 1,190 deaths per 100,000 males. However, this difference disappeared when death rates were compared for specific age groups, where the rate is higher in Southampton for the older age groups. This higher crude mortality rate in Bournemouth occurred not because it's a less healthy place to live than Southampton, but because, being a town to which people retire, it has a more elderly population. This example shows the dangers of making causal links based on comparisons of crude rates. The problem can be overcome by comparing characteristic-specific rates like the age-specific groupings in this table. In epidemiology, this is known as stratification. But the presentation of stratified data can become rather cumbersome, and it's often helpful to derive a single summary rate that can be useful for comparison purposes. Adjusted rates are summary rates that have been modified to remove the confounding effect of one or more factors. Methods for adjustment include standardization and regression analyses. The resulting adjusted rate is an artificial rate that describes the rate that would have been obtained had the underlying structure of the study population been the same as a standard population. This artificial rate allows for comparison over time and place. There are two methods of standardization: direct and indirect. Direct standardization entails comparison of weighted averages of category-specific disease rates. the weights being equal to the proportion of people in each category in a convenient reference population, such as the world standard population. This direct method is used for large studies. In smaller studies, specifically when age-specific data is not available for the study population, adjustment is completed using indirect standardization. It uses age-specific rates from a standard population, for example Ontario, to derive the expected number of events in a study population, for example a public health unit. The ratio of actual events to expected events is known as the Standardized Mortality Ratio, SMR. Page 98 through 103 of the course text demonstrates how to calculate adjusted rates using these standardization methods. To summarize, crude rates are overall summary rates and are easy to calculate, but our ability to compare crude rates between different populations is hindered when the structure of the population differs by relevant variables, a phenomenon referred to as confounding. Although both approaches are associated with some disadvantages, specific and adjusted rates account for these differences in populations, thus permitting comparisons in rates. Often, when rates of disease are reported and compared, they are sex-specific and are adjusted for age, as illustrated by this graph depicting the age-standardized incidence and mortality rates from cancers in Canada from 1984 to 2014. From briefly looking at this graph, we can see that cancer incidence and mortality is higher in men, as depicted by the blue and dark grey lines, and while mortality rates have slowly decreased for both males and females over the past 30 years, the incidence rates appears to be increasing in women. Graphs like these, together with tables of adjusted rates, can help epidemiologists describe disease by person, place, and time. Chapter 5 in the course text describes this more fully.